Dear students, today I'll be starting with this type 1 sedimentation. This will be a fill problem. Okay, this is a very practical fill problem. Now, let's imagine that there is already, say before the questions, I'm going to explain it. There is already a grid chamber that is exists. Okay, say for example, this is an existing type 1 sedimentation. Okay, it's already existing. Now, the water is coming every day like this. Okay, so this existing was designed with SOR is equal to 25 meter cube per meter square per day. This was designed with 25 meter cube per meter square per day. Okay, so this is the existing one. Now, you being in environmental engineering, you being in civil engineering, I said, sir, madam, please, during this rainy season, this type of water is coming with a lot of impurities. Maybe. Okay. So, you please check what must be the efficiency of this grid chamber, which I designed already by the engineers existing, based on this water characteristics. So, the thing is, water characteristic will be given. Okay. So this water characteristics is given. Given means being an environmental engineering, civil engineering, you have to find out the incoming wastewater at present right now. And you please find the efficiency of the grid chamber that was designed already with 25 meter cube per meter square per day. Okay. So what is the first thing you will do? First thing what you will do is simple. You have taken a column. This is in the lab. Okay, you have taken a column, you put the water over here, these are your water, you take this depth as, so if you take it from here, then this depth is say maybe 2 meter or 1 meter or 1.5 or 2 meter. How many meter you should take? The thing is, you should take the exact depth of the existing plant. So since you want to check this experiment, you will check what is the depth. This depth is happen to be 1.8 meter already existing. So what we'll make is this one, we'll make it as 1.8 meter. Okay. If the existing plant is 2 meter, you have to test it for 2 meter. Now it is 1.8 meter, so we tested it for 1.8 meter. So settling characteristic for that will be same. Okay. Now, so question is clear. And what you have to do in the lab observation is, very simple thing. Now, this is a time. So you will try to collect the sample from the bottom. Okay. But mind you, this will be completely up to here. This is sludge. So when you take out a sample, simply what you do is, after 0 minute, estimate, after 30 minutes, this is the remaining concentration. In milligram per liter solids. So then you try to estimate, I think after, it's up to you. I'm just trying to get it from some textbook. So after 80 minutes, after 100 minutes, and then after 130, 200, 240, 420. Okay. The question is, you keep on observing it. So after 30 minutes, you observe, then 80 minutes, then 100 minutes. In the first one, what you got is, let's say this is 300. That means the initial concentration of the incoming solid is 300 milligram per liter. So initially this was 300 milligram per liter at 0 time. Now after 30 minutes, we estimated the sample from here. Okay, this is the outlet, but here everything is going to settle down. We are checking what is the concentration over here. Okay, so the first concentration is, how much we got is, say 189. 189 means 111 milligram per liter has already settled down. After 80 minutes, after some time, definitely the concentration will further decrease. So it is 180, 168, 156, 111, 78, and then 27. Okay. So with the time, the concentration changes, and after 420 minutes, that is, after a time of 7 hours, we find that the concentration left is only 27. That is 273 milligram per liter has already settled down. Okay. So this is the experiment you have done in the lab. Okay. Now, as I told you already, your question is, you have to find efficiency at SOR is equal to 25 meter cube per meter square per day for a depth of 1.8 meter existing plant. Okay, this is the experiment you do. From here we are going to estimate. Now this question comes in the part of partial removal. Okay, now for partial removal, what we have the idea is, number one, those particles, I'm just reminding, particles whose SOR is equal to or greater than 25 meter cube per meter square day, this will be 100% removed, correct? Number two, particles whose SOR is less than this design value of 25 meter cube per meter square per day will be removed in partial. And this partial removal is nothing. That is velocity, settling velocity designed by velocity design into its x or del x. Okay, x means its concentration. Okay, that's what we have done in the last class. Now using this method, we are going to do it. But the one thing, let's see over here, the unit of this one is in minutes. From this experiment, neither we have the velocity, only the SOR we have. Design one. Concentration remaining we have. So how to proceed the program? Okay, I think the concept is clear. Now I'm not solving the problem till yet. What I'm doing is I'm trying to explain you what is the objective of the problem in what circumstances, so that if I ask you in different formation or different configuration, you can explain the numericals. Okay, so simple. What you have to remember is SOR should be greater than 25 meter cube per day or equal to, those will be 100% removed. Those less than the design SOR will be partial removal, that is settling velocity by design velocity into the x, the concentration over there. Fine. Now from here, how will you find it? Then come back. Okay. So first thing, what do we do is, now from the same graph, you have to find another table. This is step number one, this is step number two. Now, what we want to find is, we have to make the del x and we have to make the settling velocity. Okay, so this is del x, this is settling velocity. Now see, if time is equal to 0, what is del x? Del x is equal to nothing, ct by c naught. Ct by c naught means the present concentration. This is nothing, ct by c naught means this will be the c naught. Am I correct? Initial concentration. So this del x is also called fractional concentration. Fractional remaining. Remaining means it is lying in the water concentration. Okay. So see here. This is 300 by 300 here. At settling velocity, nothing is there, so you don't have to worry for this. Now, for this part, again you may ask me, what is settling velocity? Settling velocity is equal to distance by time. Distance is equal to total depth, what we considered during the experiment is 1.8 meter. So 1.8 meter by what is the time taken is your settling velocity. Okay. So here we are not going to estimate by Stokes law. We are not estimating for a particular definite size, but rather for the whole concentration. So first thing is depth. This depth will be, so this settling velocity will be 1.8 meter divided by, what is the time? 30 minutes. Is it okay? This is the settling velocity of this particle, and this one will be 180 divided by 300. Okay, similarly here will be 80 divided by 300. This will be 1.8 divided by 80 minutes. Okay, so let me write again here for your own convenience. So this is 189, this is 180 divided by 300, this is 1.8 divided by 80 minutes. Okay, settling velocity, the unit is meter per minute. Del x is, it's a ratio of the same concentration, so no units. Okay, so let me shortcut it because already I have to solve numericals. I'm very sorry. This should be 60. Okay, 60 minutes. So 189 by 300, we get 0.63, and this settling velocity is 3. Means meter per minute. This meter is 1.8 meter by 30 minutes. Let me see the calculator. It is also take time sometimes to find a calculator. Where's my app? So this is 1.8 divided by 60. So what we do is, here we make it into 10 to the power 2. sorry, minus 2. Okay, the answer is 0.03, 0.03, but let's make it 3 for easy graph into 10 to the power minus 2. Okay, so this one is 180 by 300, correct? 180 divided by, this is 0.6, and this one is 1.8 by 3. This is 2.25. 2.25. For this, there is 100 by 300. This is 33, 0.33. This is 1.8 divided by 1.8 divided by 100 minutes. So this is, I'll say 1.8. Okay, so let me shortcut it, let me copy from the book to make the things easy. 2.5 to 100. That is distance by time, 1.8 divided by 100. Sometimes I find a textbook wrong. Let me also check. Then 130 by 156. That is 180 by 130 divided by. So this is 43. 63, 60 mass fraction remaining in 100. 168. 168. 0.56. 130. Total 130. 43. Yeah. 130 divided by. This is 0.43. Textbook is wrong. The next one is 200. 200 divided by 0.63. 0.63.6 is correct. 0.56 is correct. After here, it is not correct. 200 by 300. Or this is 66. Oh, so where are they? 160, 168. 168 divided by 300 is 156. 156. 156 divided by 300. 0.52. This is 11 divided by 300. 0.3778 divided by 300. 0.26. Then this is 0.09. Settling velocity is 1.8. It's correct. 101.8. Distance, split scalar distance by time. Distance is 1.8. 1.8 divided by 100. This is 1.8 is correct. This is the distance by distance. What is the distance? 1.8 divided by 130. 1.38. Distance 130. 1.38. Okay, this is distance by time. This is 1.9. This is 0.9. This is by time. 0.75. Point 0.42. Okay, textbook has got some mistake. Let me rectify it here. 0.4, this should be 0.42 and this should be 0.75 and 1.38. Okay. Distance by time 1.8 by 80. Anyway, now see over here. This is the graph, okay? So this value you have to, this is the first observation. From here you have to find del x and del v. And what you can do over here is, you write here settling velocity versus del x into del, and this is del x into vs. Okay, so what is settling velocity? Settling velocity is, this can be in terms of 10 to the power minus 2, let it be. So number one is 3, 2.25, 1.8, 1.38, 0.9, 0.75, 0.42. In this time, 3 is, the del x value is 0.63, 2.25 it is 0.6, 1.8 it is 0.56, 1.38 is 0.52, 0.9 is 0.37, 0.75 is 0.26, and last one is 0.09. Okay, now we have to find the product of these two values. 3 into 0.63. Then this can be 3 6 is 18, 8 1 carry, 3 6 is, sorry, 3 3 is 9, 3 6 is 18, 1.89. So this is 2.25 into 0.6 is equal to 1.35. This is 1.8 into 0.56 is equal to 1.008. There's 1.38 into 0.52, 0.71, 0.72. I'm making a decimals round off. 0.37 into 0.9 is equal to 0.33. 0.75 into 0.26 is equal to 0.195. 0.42 into 0.09 is equal to 0.037. Okay, this is the value we have got. Okay, now I think with this one we can rub it off. Actually, you have to draw this one with a graph which should be very, very accurate. Since my whiteboard doesn't have a proper graph, let me give you the rough estimation over here, okay? Okay. Now, number one, your your design SOR is equal to 25 meter cube per meter square per day. Since everything is in terms of meter per minute, you have to convert this as 25 divided by day should be converted. So 24 hours into 60. This is in terms of, I'll say, meter per minute. 25 by 24 into 60. 25 divided by, this is 0.0173 meter per minute. But what we do it over here is, this is into 10 to the minus 2. So this is same as 1.73 into 10 to the power minus 2 meter per minute. Okay. Now this is our SOR. That means those particles whose SOR is equal to or greater than this one will be completely removed, remaining will be partially removed. So from that point, what we can see over here is some removal will be over from here. But we cannot find exactly where is 1.73. We cannot exactly find it out. So we have to draw from the graph. Okay. So now the graph is something like this. This is X and this is Y. Okay. Now what you can see here is the unit are 1, 2, 3. So the best part is what you do is roughly 1, 2, 3. So let me make it this one. Let me make it around 20 centimeter. This is 1, this is 2, and this is 3. This is 1, 2, 3. This is going to be settling velocity into 10 to the power minus 2. Okay. This is the fraction. Fraction is till 0.73. So this is a fraction from 1 till around 6. So to make the things more accurate, let's make this one 6 means this is 30. So let's make this one as around 0.6. 0.6. Look here properly. This is 1, 30. 6, 5, 35. 1, 2, 3, 4, 5. Okay, now it's done. It's done. Let me make a check whether the video is still on or not because my microphone falls down. It's there. So this is your del x. Okay. This is 0.1, 0.2, 0.3, 0.4, 0.5. And this is your settling velocity in terms of this one. Okay. Now we are going to draw the graph between these two. The first one is when the settling velocity, sorry, let's make it from here. 0.42. 0.42 means this is 1, this is 0.4, 0.5. So 0.42 maybe approximate. 0.42, the value is 0.09. So can I say something around here? Okay. 0.1, this is almost 0.1. Next one is 0.75. 0.75 means this is half, this is 0.75. So 0.75 is 0.26. 0.75 is 0.26 means, or in here, here. 0.26. Then 0.9, 0.37. 0.9 means here, this is 7.5, 0.9 may be around here. This is 0.9, 0.9, 0.37. 0.37 means this is 0.35, 0.37 will be around here. So let's make it up to here like this. And this part, so can I make it around here? Yeah. So it is around here. Okay. Then 1.38, 0.52, 1.38. This is your 1, this is your 2, this is your 3. Now 1.8, 0.56, 1.8 means very close to 2. 1 and 2, 1.8 means 1.8. So here. Okay. So 1.8, 0.56. 0.56 means 0.5, 0.56 means here. So 1 point, I said 1.8. Almost right. So it may be around here. Then 2.25, 0.6. 2.25 means this is 2.5. This is 2.5 means this is 2.25. Correct. Middle one. So this is 2.25 and 0.6. 0.6 means exact. So somewhere around here. And then 3.63. 3.63. 0.6 is over here. 0.6 to 0.65. 0.63 below. So tentatively point from 3. If I go up like this, so it will be around here, higher. So these are the values of the y-axis, sorry, x-axis, and these are the y-axis. Okay. So finally, what we will draw is we will draw a freehand curve. Okay. That's all. This is a graph that is drawn between the settling velocity and the fractional removal del x. Fine. Now from here, our SOR value is 1.73. Now 1.73 is where? Where is our SOR of 1.73? This is 1. So 2. This has to be very accurate. 1 to 2. 1.73 means 14. Around here. This is 1.8. You can see over here 1.8. So 1.8 is this one. 1.73 is here. So I'm making a graph from here. So this is. And what is this value? This value is it should be less than 0.56, no doubt. So can I say this is around 0.54? Okay. And this is equal to 1.73. Is it clear? So that means from our experiment, what we have observed is for the water of such characteristics, we have drawn the diagram. We have observed that at a settling velocity of 1.73 or SOR of 25 meter cube per meter square per day, the removal will be 0.54. I mean, 0.54 will be left. Okay. Now let me do the calculation. So number one, at SOR is greater than or equal to 1.73 meter per minute into 10 to the minus 2, concentration left is equal to 0.54. Okay, therefore removal is 1 minus 0.54 is equal to 0.46 is equal to 46%. That means 46% is completely removed. Okay? At certain velocity of 1.73, the concentration left is 0.54. That is lying into the sample. That means 1 minus 0.54, that is 0.46, that is 46% has already settled down. So, the settling velocity of 1.73, 46% has been completely removed. This is part 1. Now, our next step is to find the partial removal. Partial removal. Partial removal is equal to summation of, I told you, Vs by V design into del X. So, we have to find this part from this graph. Is it clear? Have a look. Let me explain once more again. As I explained you, the removal is of two types. One is completely removable, one is partial removal. At a certain velocity of 1.73 meter per minute into 10 to the power minus 2 or SOR of 25 meter cube per meter square per day, the concentration left from the graph is 0.54. That means 0.1 minus 0.54, that is 0.46 has already been settled down. Okay, that means 46% is completely removed. Second part, the partial removal, we always know it is the ratio between the setting velocity and the design velocity into the del X. Del X means how much concentration is left over here. Okay, so from here we are going to estimate. Now, since this part 0.6, so we cannot estimate from here because we don't know this 1 point, the settling velocity of 1.73 lies over here. We have no idea, right? So we are going to estimate everything from this graph. So this value can be now removed. Now, what we will do is this graph will break into small pieces. Okay. What we will do is you can take it as per wish, del X. So you can break it into I'm just dividing into equal intervals to make the things easy. Okay, so what we are doing is we are trying to find the area of this part. That is del X into del V. Del X into del V is nothing. Del X into del V is nothing. The product of these two. Okay, so over here what we observe is, say for del X, just make it 0.5. Okay, so this can be, let me enlarge it, this can be 0.5, sorry, 0.05. So in this part, what is the del V? Is that clear? For this del V, what is del X? We have to take the mean average. Say for example, it has to be very minor. For the most easy part, let me take this part. This part 0.35 and this one let me take. Okay. Here the del X is 0.05. That is 0.25, 0.3. Del x is this one. 0.3 minus 0.25 is equal to 0.05. Okay. If you take this part considered, what is the, this is the middle. I'm taking this part and this part. This middle, what is the settling velocity? You check over here. Okay. The settling velocity over here is, maybe say, so the settling velocity from here to here is, this is 10. So roughly I'll say this is 10. Okay. No, this is not 10. This is 1. This is 0.5, 0.55. This is around 0.55. This is 1. This is 0.55. So what happened is, you have to again make the graph between the two. What is del x, what is del v, and what is del x into del v. Okay, so one example I'll plug in between. That is, del x is 0.05, this part. And what is del y? Del y is 0.55. Is it okay? 0.55 is the settling velocity, whereas the del x is this part. Is it okay? So similarly, the higher part, I'll choose another one, 0.4 and 0.45. Now I'll go with this section. Now, this is also, the width is 0.05. You make it equal width, okay? So, but what is this graph? For this one, this part, the middle part is here. Please have a look. The middle part is here. So this center, you can stretch down over here. And this is the value. This value is around, say, 1.1 maybe. I'm just taking average. So this will be 1.1. Is it clear? So for every del x, the average, if you have considered this as this is a del x, then the middle part have to be brought down, and this is the settling velocity. Is it okay? So similarly, del v, del x, everything has to be multiplied from here till where? Our design is up to here. So you have to do it up to here, not this part. Okay, so let me cover the remaining value from textbook. So what we observe is, they have taken sometimes as 0.06, settling velocity is equal to 1.5. Could you please check it out? And then another one is same with 0.06, it is 1.22. And 0.1, it is 1.00. So let me rough my graphical value. Then again, another one is 0.1, it is 0.85. Then 0.1, 0.7, 0.06, 0.48, 0.06, 0.16. And the product is, this is from the book PV and Rowe. The product is 0.09, the 0.07, 0.1, 0.09, 0.07, 0.03, and 0.01. Okay, and the summation is, total summation is 0.46. Okay, now as I explained you, they have taken 0.1, 0.1. 0.1 means you can take it from 0.2 to 0.3 also. Another 0.1 is 0.3 to 0.4. But when the graph is becoming very, very, very linear, they break it into 0.06, 0.06 part. So when the graph is very, very linear, you can make it into small fraction, top and bottom. The middle part is very steep. So they take it average as point 0.1, point 0.1, point 0.1. So you draw the graph, my dear students, and then you submit it. So during my next class, when interacting in Google Meet, I'll explain it much better. Actually, this problem, it takes sometimes more than 2 hours in the numerical in the class. I'm explaining everything in the video itself, and it's not a two-way studies. So limitation is there, and if any confusion is there, please don't be hesitant to come forward to me. Okay. So I think up to here it's clear. Now from this, the final calculation is so. So final is removable total. What we said is equal to, we said 1 minus x. It is as per the textbook, plus del x del v by v. Sorry, summation. Okay. And this part is the complete removal, and this part is fractional removal. What is x? This is x. So it's equal to 1 minus 0.54. This you will obtain as 0.46 plus the summation is 0.46, right? So 0.46 divided by, what is the settling velocity design? 1.73. That's all. So this is 0.46 plus 0.46 by 0.46 by 1.73, 0.26. Okay. So this is just like 46 percentage plus 26 percentage. It's called to 72 percentage. This is the fractional part, and this is the actual part, complete removal part. So total removal is 72%. Numerical is over. So let me repeat the question again. For an existing grid chamber of design SOR value of 25 meter cube per meter square per day, which is constructed with 1.8 meter depth, what will be the performance of the reactor if the incoming water characteristic is like this? Correct? What we do, we collect the samples, we do settling analysis tests in a lab at 1.8 meter depth, we find the settling velocity at different time, we do analysis, we calculate, and finally we know that the SOR design value is 1.73, and therefore based on this we have two removable. One is higher than SOR 1.73, that is 46%, and those below settling velocity, partial removal of this value, that is coming as 0.26, 26%. Therefore the total removal, the total efficiency of the plant will be 72% based on the incoming water characteristics, right? Please don't be hesitant. During the class, you can always ask all the questions. I'll give you more time. This itself, I used to ask the students to calculate and give it to me. Here I'm solving myself, somewhere, some value I copied from the notebook because of time constraint in the video. So if any issue is there, I apologize over here. So with this, I completely finished for sedimentation type 1. And this question sometimes I find in some textbook of BTech, but usually this is not for BTech level. Okay. Thank you.